Now that we have an understanding of redox chemistry, voltaic cells, and electrolysis, we're going to have a look at actual technologies useful to us today as we power our electronic devices and so forth. We're going to start with the lead-acid cell, a cell that's commonly found in automobiles. It is a key component of the battery that's used to start cars. Recall again the difference, though, between a cell and a battery. A battery is always a collection of two or more cells. The lead-acid cell is capable of electrical pressures of around 1.2 volts. And if you place 6 of these together, why, you get your full 12-volt battery. Okay, now, the lead-acid battery has actually a very long and distinguished career. It is a battery that is rechargeable. Now, that is important because that means it's reusable. We refer to rechargeable batteries as secondary cells. Secondary cells are cells that can be recharged. Okay? The lead-acid battery or cell is also very old technology. And old technology usually means cheap technology because the infrastructure is already in place to make these batteries in a very inexpensive fashion. Lead-acid batteries are also 100% recyclable. A very important piece of information as we look for products that don't affect us in the future for too far out anyway. The plastic case of a battery, the lead plates inside the lead-acid battery, the sulfuric acid, everything is is recyclable. The lead-acid battery is also, and unfortunately, very heavy. It is a very heavy battery, as anyone who's ever had to lift one out of an automobile is aware of. Consequently, an important term pops up with respect to these cells and batteries, and that is the energy density. The lead-acid battery has what's called low energy density. Now, the energy density refers to the amount of energy that you can get out of the battery per kilogram of battery weight. And because these lead-acid batteries weigh so much, their energy density is quite low, and low to the tune of about 0.14 megajoules per every kilogram of battery weight. A fairly low energy density, mainly because the batteries, why, they're made of lead, and lead is a very dense element. Consequently, these batteries tend to be very heavy, and that contributes to this low energy density. Now, the actual chemistry involved in the lead-acid battery can be described in the following way. We have as reactants, we have lead and lead oxide. These are both solid materials that coat the lead plates. We have 2 bisulfate ions, HSO4 minus. They're floating around in the liquid that the plates are immersed in. We have the 2 hydrogen ions that were originally attached as the sulfuric acid. And then we have, those are, by the way, the reactants. And we also have on the product side these things. We have 2 lead sulfates, 2BbSO4, and these are solid. And we have 2 waters. And then we have the very important energy that is released. This is a process that, as reactants are converted into products, produce energy. And so the way I've written the reaction, as it is right now, this reaction has been written from left to right as if the cell were discharging. Now, a cell that is discharging is releasing energy, and the electrical energy in this case is what we use to start the car with. Okay? And so literally, as you start your car, or as any lead-acid battery furnishes energy for a process, we have lead and lead oxide and sulfuric acid being converted into lead sulfate, water, and the release of energy. But as I mentioned, that this is a secondary cell, meaning that it can be charged up as well. Now, to be charged means to convert all of the products back into reactants again. And so the reaction that takes place if the cell is actually being charged is just simply the reverse reaction. And I'm not going to write it all out for you again here, but the reverse reaction in this case is the reaction that takes place as this battery is charged up. In other words, if you hook the battery up to a charging source of some sort, you are converting the lead sulfate into sulfuric acid, lead oxide, and solid lead again, returning what was a product back to the reactant side, at which point the battery, once it's charged, is ready to deliver energy to the environment once again. That's the short version of how a lead-acid cell operates and the chemistry that's involved. Now, lead-acid cells, as I've mentioned, are really very heavy, and the last thing you'd want to be doing is carrying around a lead-acid cell for your cell phone or for your laptop computer. It simply weighs too much. Enter in a new type of cell. This is a cell that's been around now for a couple of years. It's called the lithium-ion cell. And the lithium-ion cell is a cell that is relatively new technology. We find it in cell phones, and we find it, of course, in laptops, and it's what makes these devices light enough to lug around. And what's interesting about the lithium-ion cell is that it generates electrical pressure of about 3.6 volts, quite a bit more electrical pressure than the lead-acid cell can produce. This additional electrical pressure is something that is to our advantage if we have devices that need to be powered by higher voltages. The lithium-ion cell will require fewer of these cells if we need a higher voltage. In any case, the lithium-ion cell is rechargeable. This is a good thing. It can be used, as the lead-acid cell was, over and over and over again. It is an example of a secondary cell, as it is rechargeable. Okay, so far a lot of similarities. The thing about lithium-ion cells, though, is that they are considered new technology. And consequently, new technology, because the infrastructure doesn't exist to make these devices as cheaply as we would like, these cells tend to be expensive, although over the last couple of years their prices have come down quite a bit. As far as recycling goes, the verdict is still out. It would be better to be safe and to deliver your used lithium polymer cells to your local county recycling centers where they can be recycled properly, rather than just deposit them in a garbage can. Now, here's an important difference. Unlike the lead-acid cell, the lithium polymer cell is lightweight. The lithium cell doesn't really have anything in it that has high density, like the lead cell. Lead in that case. Lithium is a very lightweight element, one of the lightest weight elements around. Hence, these cells tend to be very, very lightweight. And consequently, they have what we refer to as high energy density. Energy densities range over several different values, but just as a rough guess at the energy density of a lithium-ion cell, it's about 0.46 megajoules per kilogram. And if you compare that to the energy density of the lead-acid cell, what you can learn from this is that per kilogram or per weight, a lithium-ion cell has roughly 3 times the amount of energy stored inside it. This is a significant savings and makes it possible for us to have lithium-ion cells in everything from cell phones to rechargeable tools and that sort of thing. Now, the chemistry that goes on, it's kind of interesting. We're not going to get into the real details here, but I'll give you an abbreviated chemical reaction. It's actually a lithium cobalt oxide material that's used. It's a solid, and the reaction is between it and lithium carbide, which is also a solid. And I'm showing you, in this case, the discharge reaction. And the products that form look very similar to the reactants. We still have a cobalt and oxide that's formed. This is a solid as well. And lithium carbide, but this time with only one lithium. This is a solid. And then finally, because this is a cell capable of generating energy, we'll include energy here as a product. Now, the discharge reaction converts the reactants into products, and the charge reaction, which I'll write here, would require an external source of energy, but we could convert the products back into reactants again. And so it's the same process. Left to right is the discharge reaction and is what produces energy, and then to return the battery or cell to its original charged state, we need to supply energy and reverse this reaction in just that way. Now, just to convince yourself, too, that this is a redox reaction, it doesn't hurt to go through and identify important oxidation numbers and changes that we observe. If we focus our attention on the left-hand reactant, the oxygen in this case is a -2, and there are two of them, just like that. The lithium is a +1, and this leaves us with a cobalt, which is a +3, in order to make everything work out right and for everything to be neutral. Moving on to the second reactant, the lithium in this case is still a +1, and we have two of them, but the carbon in this case is going to be a -2. Moving on to the products, lithium isn't changing. Its oxidation number, just like the oxygen, isn't changing. Oxygen's a -2, oxygen's a -2 again, but this leaves our cobalt with a +2 oxidation number. Needs to be that way to keep the entire solid neutral, as it's supposed to be. And then the final product, the lithium carbide, this lithium hasn't changed at all. It's +1, but the carbon has in fact changed. It is now a -1. Based upon these oxidation numbers, we can say that the carbon has undergone a change in this process. It's gone from a -2 to a -1, and this process is oxidation. As the cell discharges, carbon is oxidized. The other change that takes place is that for the cobalt starts out with a +3 and winds up with a +2. This process is reduction, and the cobalt is reduced. And really, how does this change take place? Well, if you're just looking and tracking things, you'll identify the fact that in this process, one of the lithiums on the lithium-2 carbide actually winds up migrating through the cell across an insulating layer and winds up attached to create two lithium cobalt oxides. The operation of the lithium-ion cell is really just the migration of lithium ions as they leave one reactant and join the other. The charging process reverses their flow. Now, the last example of energy-producing redox technologies that we'll look at is the hydrogen fuel cell. Now, the hydrogen fuel cell has an interesting history. It is efficient. It creates energy very efficiently. It is clean. Okay? It is also relatively lightweight. Okay? But it is old technology. And normally you would think that this would mean it would be an inexpensive technology, but it also winds up being, for reasons we'll get into in just a moment, quite expensive. And this is really the hurdle to using, this is one of the hurdles to using hydrogen fuel cell technology. The hydrogen fuel cell requires, to be useful, hydrogen gas. And hydrogen gas is a bit of an issue. It's difficult to transport, it's difficult to store, and it also happens to be very explosive. A lot more explosive and more hazardous to dispense than ordinary gasoline would be. So it's just something to be aware of as hydrogen fuel cells are talked about in the media and in the news, there are some real issues associated with hydrogen fuel cells, but we'll take a look at them here today anyway. Now, the chemistry couldn't be simpler. The chemistry of the fuel cell is simply that two hydrogen gas molecules combine with one oxygen gas molecule. That looks fairly simple. And as it discharges, produces water that is warm enough to be released as a gas, but you could think of it as a liquid. And then, of course, there is the energy that is released. All right? And if you were to charge this cell, you would just convert, in effect, the liquid water or gaseous water back into hydrogen and oxygen. And this is an electrolysis process where water is electrolyzed to create hydrogen and oxygen, which can be then used again as fuel. Now, we're going to concern ourselves here with the discharge part of the process, and what I've drawn for you here on screen is a schematic, an overly simplified version of the fuel cell and how it operates. Now, on the left, what we have is an electrode. Now, this electrode is actually graphite, or some conducting material that is not going to participate in the reaction. And we also have graphite over here on the right. These are the electrodes that actually will be the materials through which the electrons will pass. And we're going to attach one of these electrodes to one side of the light bulb and the other side of the light bulb to the other electrode, just like this. And so our light bulb will simply bridge the gap between the two graphite electrodes. Now, on the left-hand side, we're going to have the process of oxidation. Oxidation, as you know, is something that produces electrons. And the oxidation process that produces the electrons looks like this. We have two hydrogen gas molecules, and what's formed are four, let's choose a different color for that, four hydrogen ions and four electrons. Now, it's clear from this that we need a source of hydrogen gas. Hydrogen gas is going to be turned into the electrons and the protons that we need to make the cell operate. And so the hydrogen gas is actually blown into this region right here. And while we're at it, let's just take care of the oxygen gas that goes into this region right here. And so the fuel cell is going to use hydrogen and oxygen gas as the two components to make the energy. And the purple piece that you see here is a divider that keeps the oxygen and the hydrogen from mixing together. And so the hydrogen gas comes into contact with the graphite electrode on the left, and the oxygen gas is coming into contact with the graphite electrode on the right. And so on the right we have the reduction process taking place. And it's going to be the reduction of oxygen gas. And so we're going to have oxygen gas combining with four protons and four electrons to make two water molecules. Now, if you combine these half reactions, the oxidation and reduction half reaction, why, you'll be left with everything that I have up there labeled as chemistry, the overall net reaction in this case. Well, let's return to the left-hand side and make some identifications. Where there's oxidation taking place, there are electrons being produced. And so the electrons are produced in the graphite electrode, and they emerge from the graphite electrode and travel up the wire like this. This electrode where oxidation takes place would be referred to as the anode, and it would be identified with the negative sign. On the right-hand side, we see that electrons are actually required as a reactant, and so the electrons continue their way after having passed through the light bulb into the right-hand graphite electrode, where they join up with the oxygen and hydrogen ions that are there to make water. This place, in this reaction where reduction takes place, this is known as the cathode. And the cathode is labeled with a positive sign. And so our fuel cell has some of the conventional terms that apply to it, identified with where oxidation and reduction are taking place, namely that where we have oxidation, we have the anode, and where we have reduction, we have the cathode. However, to finish off this description of the fuel cell, I'd like to point out that we wind up on the left-hand side of the cell with a bunch of hydrogen ions that are produced. And these hydrogen ions begin to fill the space around the graphite electrode. To make matters worse, notice that the hydrogen ions are actually required for the reduction process to take place. And so these hydrogen ions need to migrate, but getting in their way is this divider. This divider that keeps the hydrogen and oxygen gas separate from one another, required to be there because we don't want hydrogen and oxygen mixing together. That is an explosive mixture. The divider must somehow keep hydrogen and oxygen gas molecules apart and yet let the hydrogen ions through. And special polymer membranes have actually been created to make this happen. They are a porous membrane, and so I'm going to make my membrane now porous. But the pores are so small that the hydrogen and oxygen molecules cannot pass through. However, the hydrogen ions themselves are able to migrate through this porous barrier and reach the other side, where they can then combine with the oxygen and the electrons that are arriving on the cathode to create the water vapor that is produced as a byproduct. Now, tying this all up, this divider is actually known as a semi-permeable membrane. Or let's try that again, a proton permeable membrane. And these special polymer proton permeable membranes are difficult to manufacture, and for that reason are quite expensive. In fact, it is the proton permeable membrane, the membrane that keeps the hydrogen and oxygen gases apart while at the same time letting the hydrogen ions move through the fuel cell. It's this proton permeable membrane that really adds to the cost of the fuel cell and its manufacture.